Welcome, friends. Uh, Now we are going to discuss a very important thing, that is different types of quality control tools. Usually, 7 different quality control tools are used by the quality managers, and those we are going to discuss. But keep in mind that instead of these 7 quality control tools, some other quality control tools can be also used depending on the based on the requirement. The most widely used 7 quality control tools are process flow diagram, check sheet, histogram, Pareto diagram, cause and effect diagram, scatter diagram, and control charts. Okay, so let's precisely understand these things. So first one is flow chart. It is used to document the detailed steps in a process, often the first step in process reengineering. So flow chart basically depicts you the which particular it depicts the sequence of the process flow, and you can understand which particular task is to be done before or which particular task is to be done after which event. That you can understand from your process flow chart. So from the process flow chart, it is you can also identify the bottleneck of your operation, and also you can identify that in which particular workstation the defects are going on, and you need to take special care about that particular workstation. So that's why flow chart is very important, and it is a basic requirement or necessity. Then consider the checklist. What is checklist? Simple data checkoff sheet designed to identify type of quality problems at each workstation, per shift, per machine, or per operator. So in case of checklist, uh, different types of defects are addressed, and how many defects are there, that is also uh, first you give the tick marks and then you mention the numbers. For example, here in the checklist you can see that broken zipper, ripped material, missing buttons, faded color, these are the defect types, and number of defects 1 2 3 3 ticks are there. Here there are 7 ticks, 1 2 3 4 5 6 7, and here there are 3 ticks, there are 2 ticks. So checklist helps you to identify the to identify the number or the defect type, which particular defect type, how many which particular defect is occurring very frequently, or which particular defect is not occurring very frequently, or the total number of that particular defect that you can obtain from your checklist. Then there is a histogram. Okay, so a chart that shows the frequency distribution of observed values of a variable like service time at a bank drive-up window displays whether the distribution is symmetrical, or normal, or skewed. So histogram, it is a very common technique that is used in statistics, that along the x-axis the outcomes are addressed, and along y-axis the frequency is mentioned. So you can uh, from the histogram you can understand that the frequency distribution, and you can also check that whether your it is one skewed, it is symmetrical, or it is skewed, that your that you can also identify from your histogram. Okay, whether the distribution is symmetrical or not, that is that could be understood from your histogram. Then there is Pareto analysis. Pareto analysis, this is uh, another thing technique that displays the degree of importance for each element. and it is named after the 19th century Italian economist, often called the 80-20 rule. Principle is that quality problems are the result of only a few problems. Example, 80% of the problems caused by 20% of the defects. So you, along x-axis, you represent different defects, and you can see from this diagram that that most of the problems, quality oriented problems, are caused by actually very few number of causes. Very few number of causes. Most of the quality problems are for very few number of causes, and that is why that's why it is represented. For example, you can see here that suppose if you think about the E, so if this is a problem, or this is a cause of your quality loss, so you can see that the contribution to quality loss, the contribution of E to the quality loss, it is very less. It is very less, or it is least. So most of the quality oriented problems that are due to A and B. So it is concluded from different analysis. Researchers have seen that the 80% of the quality oriented problems are caused by only 20%, 80% of the quality related problems are caused by 20% of the causes. Okay. And then it is also very important, and it is quite widely used, that is cause and effect diagram. It is also known as Ishikawa's fishbone diagram, because this was derived or invented by Ishikawa, Japanese quality expert. So here the effect is represented. Suppose quality problems, or suppose welding defects. So here the ultimate effect is represented, and these arrows actually represent the diagram of these arrows represent what are the causes, and also the category of causes, like machines, workers, suppliers, temperature, process, or material. The causes are represented by these arrows, and also the category is also represented. And from here also some other these extended parts you can also find. That means in terms of personnel, what are suppose equipment related causes you can show here, or the personnel related causes you can show here, and what are the causes for these cause that are represented by this thing. What this is the main cause, and what are the causes behind it, that is also represented by these things. So in this way, it looks like, ultimately it looks like fishbone. So that's why it is termed as fishbone diagram, Ishikawa's fishbone diagram, or cause and effect diagram. Then the scatter diagram or scatter plot, a graph that shows how two variables are related to one another. Data can be used in a regression analysis to establish equation for the relationship. So here you can plot your independent variable x, here you can plot your y dependent variable, and you can see that how your scatter plots are there. Okay, so you can see here that from this scatter plots you can notice that there is an upward trend. So to understand the upward trend, or using any kind of software like Minitab or StatGraphics or any standard software, you can plot these things, and you can also see your best fitted line. The best fitted line is actually drawn or based on your regression equation. So based on that, in your regression equation, you find out the value of, there are formula for regression equation, how to find out the intercept, or how to find out the coefficients of the of your independent variables. So based on that, the best fitted line is drawn, and from the best fitted line you can see that whether there is an increasing trend, or whether there is a decreasing trend, or whether there is no trend at all. So then the control chart. This is important tool used in statistical process control. The UCL and LCL are calculated limits used to show when process is in or out of control. So control chart, this is a very common technique in statistical quality control. Control chart is widely used. For example, there are control chart for variables, there are control chart for attributes. Different types of control charts are there, and usually we, from the target value, we usually prefer 3 sigma level, 3 standard deviation to find out our upper control limit and lower control limit. So depending upon the specific case, actually, or depending upon the particular type of problem, we calculate the control limits, the upper control limits and lower control limits, and we check that whether our the given values or the estimates that actually given values or the estimates that goes beyond the control limit or not, that we can check out. Thanks for watching. I'd just like to add 2 things. I have added this slide of 7 quality control tools. The first is based on histogram. I have shown here one example that along x-axis you are representing the weights, and along y-axis you are representing the frequency. So this bar represents the weight for 132. This bar represents the weight for 134. Suppose you are measuring the weights of the students of a class, or any from any population. So this bar represents the height of 140. This bar represents height of 1. This height represents, this bar height represents the weight of 140. So what you can understand, or what you can conclude from this histogram? From this histogram, you can see that there are 2 students who have weight of 132 unit. There are 2 students who have the weight of 134. There are 3 students who have the weight of 136. There are 8 students who have the height of 140. And again, there are 3 students who have the height of 144. There are 2 students who have the height of 146, and so on. So mostly, the more you move or shift towards the mean, okay, the middle value, the frequency is also more. So this is a symbol of normal distribution. Okay, so when you will consider the problems, your data must not be your data it need not be, I mean, exactly normally distributed, but more or less it should be normally distributed in many cases. So that thing, that particular thing, you should check out. And I have also added another slide for Pareto analysis to make the idea about this thing very clear. So you can see here that along the x-axis, different types of defects are represented. And this is the example of Pareto chart of titanium investment casting defects. Okay, for casting Pareto chart of casting defects, Pareto charts are quite widely used. And you can see here that shrink, porosity, weld alloy, shell inclusion, hard alpha inclusion, or tungsten inclusion. There are different types of 1, 2, 3, 4, 5, 6 number of defects are there. And along y-axis, you are representing defect frequency. You can see that shrink has the frequency of almost 70, whereas the porosity has the frequency of 10. Weld, it has the porosity of almost near about 5 or 7. Shell inclusion, it has the defect frequencies very less. And these represents your cumulative percentage value. So you can understand that shrink alone accounts altogether these 1, 2, 3, 4, 5, 6, these 6 defects, they all 6 defects, okay, these all 6 defects comprise the 100% of the quality oriented problem, right? But you can see that shrink, this defect, it alone 70%, almost 70%, it has the defect frequency of 70%. That means that out of this 100% defects, 70% is because of shrink, and here almost 10% is because of porosity. So if you consider only the first 2 factors, then shrink and porosity jointly, they comprise near about 80% for the defects. So our conclusion is like that 80% of the problems caused by 20% of the defects. Okay, if there are suppose if it comprises 80%, so 6, there are 2 out of 6. Okay, so what is the percentage? Suppose you consider that instead of 1, 2, 3, 4, 5, 6 defects, there are, for example, 10 defects. So the first 2 category of defects, okay, 2 out of 10, that means it is 20%, 2 out of 10. So you will see that almost 80% of the defects are because of these 20% of the type of defects. So 20% of the 80% of the defects are due to 20% of the factors which are actually causing the defects. So this is the ultimate thing.